Now, I have already made a video going from the top equation to the bottom equation, so I won't be going into detail about this. However, as you can see, both equations represent the Lorentz transformation. After I discovered this, I decided to post this on Twitter, and that is where I met Austin Ryder. When I posted this to his thread, he responded back that he found the same equation, but unlike mine that uses secant, he preferred the reciprocal of the Lorentz transformation, which uses cosine. After looking at both equations, I realized that secant is used for time dilation, while cosine is used for length contraction. But before I get into these graphs, let's look at an example of time dilation using the old Lorentz transformation. The example is by openstacks.org, where they have the time at 1.2 seconds and the distance at 0. This is important because my equation can't do a distance greater than 0. The velocity they use is half the speed of light. After plugging in all of this, they get delta t as 1.4 seconds. Can my new equation give us the same exact answer? As you can see on the bottom right hand corner, highlighted in gray is my equation for delta t, and this is what I plug into Desmos.com. As you can see from the graph, at half the speed of light, the green line where x equals 0.5, and using 1.2 seconds, I get delta t as 1.386 seconds. And if I round it to the nearest tenth, I will get the same answer as 1.4 seconds. Now you can use any speed of light for x, and you will get back that particular delta t when you use 1.2 seconds. But can this work for length contraction? Yes, but let's look at another example from OpenStack.org first. As you can see from the example for length contraction, they use 100 meters for length at the velocity of 20% the speed of light. Another key factor is that the time is 0. For my equation won't work if time is greater than 0. After plugging this in, we see the answer is 98.0 meters. Can my equation give us the same answer? As you can see my equation at the top, highlighted in gray, this is what I will plug into Desmos.com. From this graph, we can see that x equals 0.2, which represents 20% the speed of light, which intersects our equation at 97.98 meters. If I was to round this to the nearest tenth, we would get the same answer as OpenStack.org at 98.0 meters. So you can see that both of these equations can graph the time dilation or the length contraction and give us the answer for any percentage of the speed of light. But can we use this idea to graph the Lorentz transformation in space-time? Maybe. But let's look at equations provided to us by OpenStats.org. Looking at the example, we see two equations at the top, where the left represents time and the right represents length or space distortion. However, to make this work for the equation on the right, we will have to switch the numerator with the denominator, and we will have to graph this in 3D. Working with the equation on the left, we will have to transform the denominator as shown in the picture, and the t's will become our z variables to be able to graph this with the second equation on the right on the previous page. Now looking at the second equation, we will need to transform what you see at the top of this page, and you can see the new equation that we will get. Note that z is time, x is space, and y is velocity or the angle. Plus the x-axis is red, the y-axis is green, and the z-axis is blue, while the time equation is a reddish color and the space distortion equation is a bluish color. So graphing this in GeoGebra.org using the 3D calculator, we will get this. This first view is a 2D representation of these equations in the xz plane, and it shows us the line of v equals c from our example. But I would like to point out that this line is really a plane that can be represented by x equals z. Now this is a 3D representation of both of these equations. Does it represent the Lorentz transformation in space-time? Maybe. I have written a book about this if you are interested. You can find a direct link to it in the description. There is also a link to OpenStats.org there too. Hope you enjoy the video.